Most programming by demonstration approaches focus on teaching the robot trajectories and different commands, like opening or closing the gripper. This is known as programming by demonstration for low-level motion. However, other approaches focus on understanding the goal of the demonstration and extracting the semantics of human operations. This is called programming by demonstration for high-level tasks. In this video, we present an approach of the later group, which allows to recognize single-arm manipulation processes, generating an action plan for the robot. This approach differentiates four levels of manipulation information. The simplest level is the sensor's data, which consists of the raw data captured by the sensors, such as the hand pose or the finger's motion. The second level is the primitive. Primitives are discretized sensor data with a semantic meaning, such as opening and closing the hand or the hand motion in a certain axis. The next level is the operation, which is the simplest manipulation action that can be performed on an object, such as grasp, insert, place, etc. Finally, the last level is the process, which is described as a sequence of one or more operations with a joint purpose, such as serving water. The system is composed of 5 modules. 3 of these modules are in charge of increasing the complexity level of the manipulation data. First, the discretizing module converts the data captured by the sensors to the primitive level. Then, the understanding module converts the primitives into operations, utilizing Markov models. And finally, the sequencing module converts the segmented sequence of operations into a process. The last 2 modules are training, which trains the Markov models of operations, and interface and calibration, which is used to guide the user and calibrate the sensors. In the current implementation of the system, 2 devices are used to capture the operator's manipulation data. However, with slight modifications, the system could be used with any other combination of sensors. The first of these 2 devices is a data globe, which captures the finger's bending and pressure values and hand orientation. Here we can see an example of the sensor's data from the data globe's SDK. The second device is a hand motion tracker that captures the position of the hand in the X, Y, and Z axis. This video shows how the user records an operation with a bottle. The first step is to calibrate the sensors, defining the direction of the X and Y axis for the hand tracker and for the data globes. For that, the user has to move the hand in the axis directions. Then, the origin of coordinates must be defined by placing the hand on it. And the position captured by the hand tracker has to be scaled in the different axes. After this, the user can select the object and the operation to be recorded, that in this case is grasping a bottle. And finally, he can start recording it. After recording a demo, it is automatically stored in the information system. In this database, the information is first classified by object and then by operation. Inside each operation, we can find all the recorded demonstrations and the Markov models derived from them. Each of these demonstrations is defined by a set of files containing the observed sequence of primitives from different sensory sources, which are called primitive variables. These variables are the hand orientation, hand rotation, hand motion in X, Y, Z axis, hand motion in Z axis, fingers bending, fingers pressure, and a complete and a simplified combination of all these files. Here we can see the different primitive variables sequences. As can be seen from this information, the three phases of the grasping operation can be differentiated: approaching, grasping, and retracting. A Markov model is defined for each operation. This way, the recorded sequences of primitives can be identified with the model with the maximum likelihood. However, the recorded sequence of primitives comes from multiple sensory sources, so a multivariate approach is used to merge their information. Therefore, a different Markov model is created for each variable, and then the final likelihood is the weighted average of all of them. Additionally, the appropriate number of previous states to consider for the transitions is not the same for every variable. Therefore, a different order will be used for each model. As a result, the final model of each operation is a multi-order, multivariate Markov model. As explained before, the manipulation database stores the Markov models of each operation. As an example, we will see how the models of the bottle grasping operation are stored. Models of first, second, and third order are created for each primitive variable. Let's take a look at the first order Demolong model, which stores a combination of all the variables. This file contains the initial state and transition probabilities between the observed primitives, that are the states, and a mapping between these primitives and the matrix indexes. This table shows the information of the previous file in a clearer way. As we can see, the most probable initial state is an XY motion, followed by stopping that motion, stopping the motion in the Z axis, rotating the hand to align the pitch axis with the Z axis, etc. Let's take a look now at the first order hand rotation model. Again, we can see the information of the model organized. In this case, the most likely sequence is starting with no rotation, then doing a minus roll hand rotation, and then no rotation again. Now, let's check one of the second order models. For instance, the model of hand rotation again. As we can see, now the transition probability is defined by different matrices. This is because now the transitions depend on the two previous states. So the index of the matrix represents the first previous state, the row of the matrix represents the second previous state, and the column represents the state to which it might transition. Finally, for the third order models, the same structure is followed, adding a third level of information. This is an overall image of the multi-order, multivariate Markov model of the bottle grasp operation. For each variable, the considered order of the model is determined empirically. As can be seen, in most cases the second order model is selected. Regarding the weight of the model of each variable, it is determined by a cost function to maximize the performance of the process segmentation. This chart shows the weight of the models of the different variables for several objects. Here we can see how the Markov models are used to recognize the recorded operation. For each of the possible operations of a bottle, the likelihood of the observed sequence of primitives of each variable is computed with its corresponding model. Then the weighted average is calculated, obtaining the likelihood of the operation. Finally, the selected operation is the one with the highest value, in this case grasp, with a 0.52 over 1. The system was tested for 5 different objects: bottles, hammers, a taping gun, a screwdriver, and cutting pliers. Here we can see the performance of the operation recognition for each object after training the system with 40 demonstrations of each operation, which were performed by 4 users. The results were very good for the bottle, cutting pliers, hammer, and taping gun, with an average recognition of 80%. However, for the screwdriver, there were problems for recognizing 2 of its operations, as they are very similar and the data captured by the utilized sensors is not enough to differentiate them. This video shows how the user records a process with a bottle. As we can see, the sensors are already calibrated from the previous operation recording, so it is not necessary to do it again. The user just needs to scale the hand tracking in the different axes, and then he can start recording the process. The recorded process is composed of three operations: grasp the bottle in location 1, pour water in location 2, and place the bottle in location 1. To segment the process into operations, the start or initial state and the transition probability timeline of the observed process are computed for the model of each operation. When a maximum is detected in the start probability timeline of any of the operations, the transition probability is evaluated for all the operations in the following time steps. If the operation with the maximum start probability has also the maximum transition probability, and it is higher than 30%, this operation is added to the segmented sequence of operations. Additionally, the system recognizes the location in which each operation is performed by checking the hand position at the time at which the operation is detected. In the previous demonstration, the segmentation of the process in operations is perfect. Therefore, the process classification is very easy. However, even with a wrong segmentation, the system can identify the process that better explains the observed sequence of operations, increasing the robustness considerably. This is done by comparing the segmentation with all the possible processes, selecting the one with the maximum likelihood. This is an example of how the likelihood of a wrong segmentation is computed for the grasp, pour water, place process. As this process has three operations, all the sequences of three operations of the segmentation are analyzed. Then, for each of them, the likelihood of each operation is calculated based on the confusion matrix results of that object, and a zero is added to penalize every extra operation of the segmentation. The average of these values is the likelihood of the analyzed sequence. Finally, the maximum likelihood is assigned to the evaluated process. This chart summarizes the results obtained for the 5 tested objects. The results are quite promising with a small number of demonstrations. The performance drops a bit for the screwdriver because some of its operations are very similar, as we saw in the confusion matrix. However, for the rest of the objects, process segmentation is perfect around 40% of the time, and process classification is correct around 75% of the time, when just one demonstration of the process is provided. Additionally, this increases to around 90% when 5 demonstrations of the process are provided. The outcome of the presented approach is an action plan for the robot. Therefore, the next step is the automatic generation of optimal trajectories for the robot based on the action plan. This work was presented in a conference paper for a cable routing use case. In this paper, all the possible operations were predefined as parameterized functions. Then, a sequence of these functions was selected based on the action plan, and the location of the operations and the information about the environment were used to parameterize them. The figures on the right show some of the results, where the trajectory is automatically generated with different action plans and workbench layouts. If you want to know more about this, click in this video.